So today we're going to be talking about two ideas that are going to go along with the last section we just worked on. It shouldn't take too long, just like the last one, there wasn't that much going on. So the two big ideas that we're going to look at today is, there's lots of names for this, and you'll see it called lots of different things, but we have what's called the least squares regression line. I'm just going to take it. We have the least squares regression line. Also known as maybe just the regression line. You may hear it called that. You may hear it called the, I call it a lot of times the LSRL for least squares regression line. You'll also see it called the line of best fit. And the idea behind this is if you do have something that appears to be linear, then you should, in theory, be able to come up with a line that represents that model. So let's say we had some sort of data that looked like this. It appears to be linear. You see sort of kind of strong positive linear relationship. And the idea is we should be able to come up with a line that models that data. We don't want to just draw a random line. Instead, we will use math to figure out what that line of best fit actually is. So there's a mathematical way to make a line that gets as close to as many points as you can possible. And there's not a better way to do that. So what makes the line of best fit is that you should be reducing how far away each of those points are from the line. So the line of best fit would be the line that if I measured every one of those blue lines, that you added all up all those distances, that's the smallest number you could possibly get. I'm going to make a new dot here just far away so you can see better, but let's say we had a dot here. This right here is called a residual. A residual is the distance a point is from the line of best fit, which we're going to talk about. That's the other part that we have to talk about, is how to calculate the residual. How do you actually find out how far away the actual value is from the predicted value? Those are the two big ideas. So we're going to come up with how to get that line of best fit. We are not going to do it by hand. I'm not going to go over how to do it by hand just because it's really, really messy. We're going to learn how to read computer output, because most of the times when you're doing this stuff, you have a computer do it and then it spits out this output, and they all look just about the same. So we'll talk about how to read that. And lastly, we'll talk about how to calculate the residual. So those are the big ideas of today. So if we look at this right here, this is the same example we had in the last set of notes, 9.1 notes. This is 9.2 if you want to write that down. Maybe where we had the GDP and the CO2 emissions, and now instead of finding the correlation and graphing it, okay, you should already have a picture of the graph of this. It looks something like this. We had a lot down here, and then you had like one here and one here, something like that. I don't remember exactly. But now that we know how to graph it, we know how to talk about the correlation. So there was a moderate, I think, or strong positive linear relationship between GDP and CO2 emissions. We can now take this and come up with a line that represents it. So what we're going to do is use math and our computer to come up with what is that line of best fit for this model. So luckily for us, it's going to be the exact same website. This is why I picked this site, because it did both. So you could just type in the numbers once and do both. So I've already typed in the numbers here to save us some time. So now instead of find the correlation coefficient, we're going to find the equation of the regression line. So LSRL, regression line, line of best fit, all the same ideas. So go ahead and type in the data, click on that dot, and hit compute. We're going to scroll down, and it's giving me the line of best fit right here. Notice that it's a y equals equation. So y equals 114.057 plus 169.042x. Except in statistics, we always like context. We want people to look and see exactly what we're talking about. So we will not be using y and x for the majority of the time. Now, there could be questions where they have y and x. That's fine. But when you're doing your own work, do not write y and x. So we're going to then go to our thing. So I'm going to make this 2 windows because I don't remember that. So I'm just going to write down the 2 numbers they were. All right, so it is 114.057 plus 169.042. Okay, so the way we're going to write this out is we use meaningful variables for y and x. So we're going to start out, instead of writing y, we're going to write what the y variable is, which is CO2 emissions. You can tell this is our y variable. Remember, the y is usually on the right or the bottom. So we're going to write CO2 emissions. Okay. And then you put a hat over it. So it's a CO2 emissions hat. The reason we're putting a hat is because this is not a real value. This is a predicted value. In statistics, the hat means predicted. So remember, we had p hat. That was the predicted percentage. It wasn't the actual percentage p. So it's not one of these values here. That's why we're not writing just CO2 emissions. It is a predicted value. It's a guess. It is the guess of where the average CO2 emissions will be. So then once you do that, we always write, and you saw that on the output that we did in our program or that website, we always write the y-intercept first. So I know you're used to mx plus b. We don't write it that way in stats. We write it as, oops, it could be y. We write it as the intercept, so it'd be b plus mx again, I guess. So we write the intercept first, so we have 114.057, that is the y-intercept, plus 169.042, and then we write our y or x variable, which is GDP. So instead of writing y and x, which can be confusing if you just look at it, because what's y, what's x, you actually write the variable name so nobody would have any confusion. So the whole point of this now is that I can plug in any GDP I want to then try and guess what the average CO2 emissions for that GDP will be. So that's the purpose of this. It's very powerful if you have a linear model, because then you can start predicting anything. So let's say we had a country that popped up, and this year it was at 4.2 GDP. Notice that we have no 4.2 GDPs here. So instead, we could, rather than trying to measure all the CO2 emissions, we could plug in that 4 point whatever I said and see what the predicted value, about what it's going to be, what the CO2 emissions will be for that country. So that's kind of one of the big parts here. So we're not doing any of the math ourselves. We're having the computer do it for us, but that is how you come up with the LSRL. I remember this is the LSRL, or regression line, line of best fits. So whenever they ask for the LSRL or the regression line, it's just an equation. You just write out the equation that the computer's website spits out for you. So now what we can do is we can use our LSRL, like I said, to make predictions. So that's what we're going to do next. This is very, very easy to do. I was thinking a way I could copy this. I don't know. So I'm going to go over here, the next slide. I'm not going to do all 3 of these. I'm only going to do one. I think you'll get the idea. It says, use the equation of the gross domestic products in trillions of dollars and carbon dioxide emissions data to predict the expected carbon dioxide emissions for each gross domestic product. So what we have here is we have 3 different GDPs. And what we could then do is, if the country's GDP is 1.2 trillion, we can then plug that into our equation to see what the predicted CO2 emissions is. So I'm just going to do 1.2 trillion, and you'll see how to do this. So if I want to predict the CO2 emissions for this, I just need to plug in 1.2 into GDP. So we have, I'm just going to put CO2 equals 114.057. This is how you show your work. Plus 169.042 times 1.2. So all we are doing is, instead of doing just GDP, we're plugging in that specific GDP. Forgot my hat. So then the CO2 hat, let's go ahead and calculate what that's going to be. So let me go to my calculator. I forgot to open it up. All right, so then I would type in 114.057 plus 169.042 parenthesis 1.2 close parenthesis, and that gives me 316.9074. So CO2 emissions is going to be 316.9074. And just like always, we have to put the units, so millions of metric tons. I'm just going to put millions of metric tons. I don't think that's an official unit, but I don't want to write that all out with the silence. So the answer to the question we had here, what's the predicted expected carbon? 1.2 trillion. The answer is we'd expect that country to emit 316.9074 millions of metric tons of CO2 emissions. Okay. So that's how we use the equation to make predictions. Once again, very, very simple. You're just timesing a number by something else and adding another number to it. And then the last thing that we have, or I guess two things, to look at how we can look at this sort of weird table thing we have right here and figure out what the LSRL is from that. There is a lot of stuff in this table. We're going to talk about that in the next section. I'm doing it now. So I'm going to read. It says a paper in a 1998 issue of American Journal of Sports Medicine examined data regarding the impact age had on a number of days after arthroscopic shoulder surgery before 10 weightlifters were able to return to the sport. So the idea here is, does their age have any relationship with how long the recovery is? Interesting idea. We're not going to talk about how we can tell that from this table. We're just going to come up first with the least squares regression line, and then we will, I'll show you how to calculate residual. So at this point, the only thing that we need, I'm going to cross out all the stuff we don't need right now. Okay, at some point we will need it, just not yet. Okay, so we don't need any of that. We don't need any of this. The only thing we need right now is this stuff right here. This actually tells us the LSRL. So up here where it says constant, sometimes it says constant, sometimes it says y-intercept. That is the y-intercept. And then usually below that, the second thing in the table where it says age, that is the x variable. And the numbers to the right, so this right here is actually going to be the y-intercept. And the number below it is the slope. So the top number where it says coefficient is the y-intercept. The number below that, where it usually has a name of some sort, is the slope. So always look for the first two columns. The first two columns of the table. Sometimes it says coefficient. It varies, but it will have usually two words. One word's constant, and then the numbers next to those are going to be the two numbers you need. So the LSRL here, so we need to look through here. We know that X is age. Okay, we know that X is age. So we need to go back through here and see what the Y is. So it's not telling me in the table, and it may not. So when I go back through this, it says examine the data regarding the impact age had in the number of days after arthroscopic shoulder surgery before 10 weightlifters able to return to the sport. So it's the number of days it took for them to get back. So maybe recovery time hat, or recovery days, something like that. But it's just how long it took them to get back to the sport, which in my opinion is their recovery. So my y variable, which I read in the problem, I didn't find it anywhere else. I had to figure it out myself. So I'm going to do recovery time hat is equal to, remember the constant is your y-intercept, the first number, so negative 5.054 plus 0.2715 age. So you get a freebie here for the most part. Usually it doesn't say x, it usually says the variable name. You just plot that with the slope. So if these two are together, these two are together, then they go together. So put the age with that number. I'll have to write that again. So 2715 age. So that's the LSRL. You'll have a table like this that you'll have to be able to read. And then the last thing we want to do, it says, is 128-year-old weightlifter took 3 days to return to weightlifting. Find the length of time that would be predicted by the regression line and then calculate the weightlifter's residual. So we've already talked about how to find the prediction. So now that we have a line, we can use that line to calculate the prediction. And this person's 28 years old, so I need to put 28 in for age. So let's go ahead and do that. So negative 5.059 plus 0.2715 parenthesis 28. That looks right. Hit enter. So it's saying it'd take 2.543 days. So I need to show my work for that. So I'm going to put RT for recovery time. So RT hat, it's equal to negative 5.059 plus 0.2715 times 28. And the predicted recovery time was 2.543. Make sure you put the units as days. Now that is the predicted time. That is not the residual. The residual is how far the prediction actually was from the actual value. So this person took 3 days. It took them 3 days. The model said it should take them 2.5 days. So the residual is how far off. So residual, which a lot of times is denoted as E for error. But if you just write residual is fine. Residual is equal to the actual minus the predicted. So the actual time was 3 days. The predicted time was at 2.5 something. So the residual is going to be equal to the actual, which was 3, minus the predicted, which was 2.543. It should come out to be 0.457, I think. And that's still days, because it's days minus days is still days. So that is the error, or the residual. The prediction was 0.457 days off from what really happened with that 28-year-old. That's not bad. That's not that bad at all in terms of the model itself. Now, there's one more idea here. Okay, we talked about finding the LSRL. We talked about reading computer output. We talked about calculating residuals. There's one other thing I didn't mention in the beginning, but I thought about and that I think you need to know, and that is the idea of extrapolation. Extrapolation is very bad. People do it all the time. Extrapolation is where you plug in X values that are outside of the data values. I'm going to show you using the last example. So let's say, for the GDP one at least, I'll go back to that. I'll go back to there. Your X values range from 0.8 to 5.9. That is the range of them. Extrapolation is when you plug in a value that's outside of your smallest and biggest. So if I plug in like 8, I would be extrapolating. If I plugged in 0.03, that would be extrapolating. It's too small. So extrapolation is wherever you plug in values that are outside of your x's. So if we go to that weightlifting example, it's a great example because age, age is very easy to extrapolate with. Like we can plug in 80. I doubt that we have data of an 80-year-old weightlifter who had the surgery and then how long it took him to get back. But even better than that, I'm going to plug in, what if you're 1-year-old? And what if you're a 1-year-old and you want to see what your recovery time would be? So what I could do then is, instead of putting in 28 for age, all right, so putting in 28 for age, I could put in 1. So let's see what the recovery time for a 1-year-old would be. Okay. So let's do the model again. So we had -5, whoops, let's put this out. We had -5.059 plus 0.2175, and let's say they're 1-year-old. So the recovery time for a 1-year-old would be -4.8415 days, which doesn't make any sense. You can't recover in -4.8 days. That makes zero sense. And it makes zero sense because you extrapolated. You put in a value that doesn't make sense. Your data values you use, it doesn't tell us in this example, but I'm guessing that they didn't use a 1-year-old. You can't put in values that are outside of the data range. Okay, so I can't put in 1, probably can't put in 2, can't put in probably 108. It wouldn't make any sense how long it would take a 108-year-old to recover. So you just cannot put in values that fall outside of your X values. And it's called extrapolation. It is very bad, but yes, people use that. They say, hey, I got this model. Let's see what happened if I did this. Plug in this number and see what happens. And it's just not accurate. Usually, you don't know if the pattern continues. You don't know if it's going to stay linear, if the slope's going to stay like that if you go outside your data range. So you just can't do it. Okay, so let's recap the things we did, even though I think I already did that. I'll do it one more time. So we talked about the least squares regression line of the LSRL. That is the line of best fit. If I have data, it is the line that gets as close to every point as possible, where the errors or the residuals are as small as they possibly can be. We saw how to calculate that using that website. We talked about how to use that to make predictions. So like I plugged in the 1.2 trillion. To see what the predicted carbon emissions was. We talked about how to read computer output a little bit, how to find the LSRL from that. Talked about how to calculate a residual, taking the actual minus the predicted. And lastly, we talked about extrapolation. And that is 9.2. So I don't think we're adding a whole bunch here. This is a pretty easy chapter. 9.3 is definitely the, has the most going on out of the 3 sections, but this is pretty much the 9.1 and 9.2. So I hope you enjoyed that. Hope you guys are all doing well. And I'll talk to you next week.